Welcome back to our discussion about verifying trig identities. In this video, we're going to run through some examples of how we use the tools that we talked about in the first part to actually verify trig identities. So we have several different types of tools to use, so there are several different types of examples. So let's start with the first one. All right, here's the first example. We have the equation secant squared of x minus 1 divided by secant squared of x, and that is equal to sine squared of x. So we're going to start this by taking that more complicated side, the left-hand side, and trying to manipulate it in such a way that it equals the right-hand side. Now, one way we can do that is to recognize that secant squared of x minus 1 is equal to tangent squared of x using our Pythagorean identity. So we can go ahead and rewrite that numerator as just tangent squared of x. Now, if I'm looking at that left-hand side now, I don't really know what I can do with tangent squared of x and secant squared of x, but I do know that I've got sine squared of x on the other side. So maybe it would be helpful for me to rewrite both of those in terms of just sine and cosine. If I do that, then I've got sine squared of x divided by cosine squared of x, and that whole fraction divided by 1 over cosine squared of x. Well, that's kind of ugly. So let's rewrite that as a multiplication instead of a division expression. So we will rewrite it so it's sine squared of x over cosine squared of x multiplied by the reciprocal, which is cosine squared of x over 1. Now, I notice right away that I've got a cosine squared of x in the numerator and the denominator, so I can cancel those out. And I'm left with sine squared of x equals sine squared of x. And that's exactly what I wanted to show. Now, this particular example has another way that you could go about it. And I started with this example because I wanted you to understand that sometimes when we're verifying, there's multiple ways to get the right answer. There's not just one road to the right answer. Sometimes there's a road that's more efficient, but taking the scenic route doesn't necessarily mean it's wrong. So let's try this in another way. Why don't we take that initial equation and break up the fraction? Since there are two things in the numerator, I can write those as two separate fractions. If I do that, I'm left with secant squared of x over secant squared of x minus 1 over secant squared of x. Well, when I go ahead and simplify that, I notice that secant squared of x over secant squared of x is 1, and 1 over secant squared of x is cosine squared of x. So I end up with 1 minus cosine squared of x. Now, if I am smart, I recognize that as a Pythagorean identity. 1 minus cosine squared of x, that's the same as sine squared of x. And I'm all done. Okay, great work, sleuths. Are you ready for the next one? Absolutely, let's go for it. Okay, next example. 1 over 1 minus sine of alpha plus 1 over 1 plus sine of alpha. Now, that is all equal to 2 times secant squared of alpha. I know that the left-hand side here is more complicated, so that's where I'm going to focus my attention and try to make it look like the right-hand side. I notice right away that I've got two fractions that have different denominators, so the first thing that I'm thinking I might want to do is combine them. To combine them, I'm going to need common denominators. So I'm going to multiply each of those pieces by a form of 1 with the other denominator. Notice that this is 1, and it is formed by the pieces of the other denominator. This is also 1 formed by the pieces of this denominator. So I'm going to go ahead and multiply these first two factors and then these second two factors. And when I do that, I end up with 1 plus sine of alpha over 1 minus sine squared of alpha plus 1 minus sine of alpha over 1 minus sine squared of alpha. Now I've got common denominators. I can go ahead and combine the numerators. And notice that when I do that, I have sine of alpha minus sine of alpha here. They're going to cancel. I'm just going to be left with 2 in the numerator. So I have 2 over 1 minus sine squared of alpha. Oh, wait. Is it 1 minus sine squared of alpha cosine squared of alpha? Yeah. And cosine squared of alpha in the denominator, that's the same as secant squared of alpha. So I end up with 2 secant squared of alpha is equal to 2 secant squared of alpha. Oh, great work. All right, next example. Let's verify this. Tangent squared of x plus 1 multiplied by cosine squared of x minus 1 is equal to negative tangent squared of x. Now, you might be tempted to go ahead and distribute that all through, and that wouldn't necessarily be wrong. But I see right away tangent squared of x plus 1 and cosine. I see lots of trig functions that are being squared. So I am thinking to myself, do I have Pythagorean identities here? And indeed I do, right? Tangent squared of x plus 1 is the same as secant squared of x. Now, cosine squared of x minus 1 is not equal to something using our trig identities. We know that sine squared of x is equal to 1 minus cosine squared of x. Well, if I negate both of those, though, I'm in good shape. So I can say that tangent squared of x plus 1 is equal to secant squared of x, and cosine squared of x minus 1 is equal to negative sine squared of x. At this point, I am thinking I might want to write things in sine and cosine on this side. Okay, and if I do that, all I have to do is take that secant squared of x and write it as the reciprocal. And if I multiply those two things together, I have negative sine squared of x over cosine squared of x, which indeed is negative tangent squared of x. And that one is finished. Great work, math detectives. Next example. Tangent of x plus cotangent of x is equal to secant of x times cosecant of x. Okay, what do you think here? I'm thinking I'm going to focus on the left-hand side here. If I focus on the left-hand side, I'm thinking I might want to write those as fractions. Maybe fractions in sine and cosine. Yeah, that looks good. So I have sine of x divided by cosine of x plus cosine of x over sine of x. Now I notice I've got two fractions with different denominators. I want to go ahead and combine them and see what happens when I get a common denominator. So I'm going to multiply this first one through by sine of x over sine of x. And I'm going to multiply this second one through by cosine of x over cosine of x. What does that look like? Okay. Now let's go ahead and do the multiplication. So this first part will end up looking like sine squared of x over sine x cosine x. And then this part will look like cosine squared of x over sine x cosine x. I can go ahead and put those into a single fraction then. And oh my goodness, isn't sine squared of x plus cosine squared of x our big kahuna Pythagorean identity? Yeah, that's going to end up being 1 over sine x cosine x. Now, I can think of a rational expression like this as 1 over sine of x times 1 over cosine of x, in which case I can just flip them both, okay? And so that gives me cosecant of x times secant of x, which is really the same thing as I have on the right. So that one's taken care of, knocked it out. Really? That's all? No, we can do more than that. We definitely have it in us to do more than that. All right, next example. Secant of x plus tangent of x is equal to cosine of x divided by 1 minus sine of x. All right, how do you want to tackle this one? Okay, as I'm looking at this, I'm noticing a fraction which seems a little more complicated than these two terms just added together. So let's think about how we might be able to tackle this. What if we use a conjugate, okay? Notice that I've got 1 and minus sine of x here, and I know that that looks kind of like 1 minus sine squared of x. Well, if I multiply the top and bottom by 1 plus sine of x, I'm definitely going to get that in the bottom. So this is called multiplying by the conjugate, and the result is going to give us something that we like. When I multiply that through, the numerator will just distribute the cosine of x through to the 1 and the sine of x. So I'll end up with cosine of x plus cosine of x times sine of x. And the bottom will end up being 1 minus sine squared of x. Well, we know that that is equal to cosine squared of x. So now let's break up that fraction into two separate fractions and simplify them, right? I have cosine of x over cosine squared of x. One of those cosines is going to cancel here, and this one will cancel out. And then this cosine of x will cancel with one of these cosines of x. And so that will simplify to look like this. 1 over cosine of x plus sine of x over cosine of x. And when we do that, all we have to do then is use what we know about reciprocal identities and quotient identities and rewrite these as secant of x plus tangent of x. Outstanding. Next example, cotangent squared of x over 1 plus cosecant of x is equal to 1 minus sine of x over sine of x. What are you thinking here? Yeah, there's a lot of different ways we could go with this one. Let's go ahead and use a conjugate again. When I use a conjugate here, I will multiply by 1 minus cosecant of x on the top and the bottom here. That will give me on the bottom 1 minus cosecant squared of x. And I'm going to just leave this not multiplied out, okay? Cotangent of squared of x times 1 minus cosecant of x. Now I know that 1 minus cosecant squared of x is equal to negative cotangent squared of x. And so when I divide out this cotangent squared of x, I will end up with just a negative 1 in the denominator. Or we can just call it a negative times that quantity, 1 minus cosecant of x. If I distribute that through, I will get a negative 1 and a positive cosecant of x, so I can write it as cosecant of x minus 1. Now, cosecant of x minus 1. Now I'm noticing that my right-hand side has a denominator of sine of x. So I'm thinking, can I write this in a way where both of these terms have a denominator of sine of x? And I can definitely write cosecant of x as the reciprocal of sine of x, so 1 over sine of x. And then if I want this to have a denominator of sine of x, I can write it as sine of x over sine of x. And then if I combine those numerators, I end up with exactly what I'm looking for. Way to go. Last example, and you may be tired of verifying by now, but we're almost done. All right, last example shows us some stuff with higher orders. Oh, tangent to the fourth of x is equal to tangent squared of x times secant squared of x minus tangent squared of x. Lots of stuff that's complicated on the right-hand side. And when you see lots of complicated stuff, it's time to think maybe we want to factor. Okay, notice that if I look at this piece separately from this piece, I could factor a tangent squared of x out of both pieces. I can treat that as a GCF. Okay, and when I do that, it doesn't look so bad all of a sudden. Tangent squared of x times secant squared of x minus 1. Oh, but secant squared of x minus 1, that's the same as tangent squared of x. And now tangent squared of x times tangent squared of x, that's tangent to the fourth of x. And we have nailed it. Great work, mathletes. And in the words of Sherlock, wow, this is getting rather fun, isn't it? I'll see you next time.